Okay, so in this video, we will be giving two different proofs of the fact that root 2 is irrational. Both of these proofs will be by contradiction, but the second of these is highly generalizable. But first, let's look at Euclid's proof, which is at least 2000 years old. So let's suppose that root 2 is rational. So it's equal to the ratio of two positive integers, and the greatest common divisor of a and b can be assumed to be 1, because if they have any common divisor, we can just cancel it out. Now, if we assume this, therefore a squared over b squared will be equal to 2, which can be written as a squared equals 2b squared, and this implies that a is even. But if a is even, we can put a equals to 2k. But then when we substitute this into this equation, the equation becomes 4k squared equals 2b squared, which we can write like b squared is equal to 2k squared, which implies that b is even. But that's a contradiction, because then GCD of a and b is at least 2, because they are both even. And by virtue of this contradiction, we conclude that our hypothesis that root 2 was a rational number is false. So this proves that root 2 is irrational. Now, as I mentioned at the beginning, this proof is not very generalizable, so we must find a way to modify this proof, or to give another proof which is much more generalizable, to prove that other real numbers are irrational. So let's look at another proof, and this other proof will involve the use of things called auxiliary polynomials, and auxiliary polynomials can be fruitfully used to prove the irrationality of many other numbers. So to understand how to use these, let's first start with the fact that root 2 can be expressed as a continued fraction like this. It goes on and on. And you can easily verify this, so you just subtract 1 from both sides, and you notice that this thing right over here is just the same as this bigger thing right over here, so you can put that equals x, and then you have a polynomial which you can solve, and you can verify that this is true. Now, let's look at the first convergence to this continued fraction. So the first convergent is just this one over here. The second convergent is obtained when you take 1 plus a half, so this thing here, it's equal to 3 halves. The third convergent, when you take this thing, you get 1 plus this, which gives you 7 over 5. And you can go on like that, and you'll find the following sequence. So this 1, this 3 over 2, this 7 over 5, and then you would find 17 over 12, and 41 over 29, and 99 over 70, and so on. And there are many things that are true about this sequence, so first of all, notice one thing. 7 is equal to 2 times 3 plus 1. 17 is equal to 2 times 7 plus 3. 41 is equal to 2 times 17, which is 34, plus 7, which is 41, and so on. So the numerators are related recursively. So each numerator is obtained by multiplying twice the previous plus the one before that. The same is true for the denominators. And this fact is not difficult to establish. So maybe we've covered that on videos on continued fraction, or maybe there will soon be videos on that. But our focus in this video is to understand how we can get the idea of using auxiliary polynomials. So, and then there's one more thing you can notice about these. So firstly, let me just summarize what we just said. So I'll call these numerators an and these denominators bn. Then we have the following. So, sorry, that's 2, that's 1, and when n is equal to 3, an is equal to 7, and bn is equal to 5. When it's 4, it's 17 and 12, and so on. And what we've just found is that an is equal to 2an minus 1 plus an minus 2, and bn is equal to 2bn minus 1 plus bn minus 2. But in fact, there's one more thing which is going to be useful for the auxiliary polynomials. It's that, so let me erase this. Notice that so if you take b squared, if you take a squared minus 2b squared for any n, notice what happens. So 1 minus 2, it becomes minus 1. If you take n equals 2, it becomes 9 minus 8, which is 1. If you take n equals 3, it becomes 49 minus 50, which is minus 1. And this goes on like that. So actually, an squared minus 2bn squared is equal to minus 1 to the n. And this fact also is proved in basic continued fraction theories. So we'll just see how we can get the idea of auxiliary polynomials here. And now notice one thing. So we don't really care about the sign of this, so we'll just take a modulus. And let me put, and then this becomes just 1. And here's how we are going to prove that root 2 is irrational using this. So let me erase all that. We have that, suppose that root 2 is rational and is equal to r over s. Then when you substitute this in this equation right over here, it becomes an squared over s times s squared minus r squared bn squared is equal to s squared. And s squared is greater than 0, so that thing is greater than 0. Now here's the important step. If you can factorize this thing as an times s minus r times bn times ans plus r times bn, and that's equal to s squared. And then you can divide both sides by ans plus rbn, and it becomes ans minus rbn is equal to s squared divided by ans plus rbn. Here's the thing. An and bn, they grow indefinitely large when n goes to infinity, because they have to satisfy this equation. So for example, if n is equal to, say, 9 or 8, then an would be equal to 577 and bn would be 408. And as you increase n, these keep on increasing on, and they are unbounded. But the thing is, if they keep on increasing forever and this thing holds true forever, then by making an and bn sufficiently large, you can make this thing right over here smaller than 1. But that's a contradiction, because this thing right over here should be an integer, and there is no integer strictly between 0 and 1. So we conclude that we have reached a contradiction, and we conclude that root 2 cannot be rational. This shows that root 2 is actually irrational. And here's where we've used the idea of auxiliary polynomials. So the auxiliary polynomial we've used here is the following. So we've used these polynomials, an minus root 2 bn, that's minus, so that's a z for a certain variable, minus z squared bn squared. These are the auxiliary polynomials that we've used in our proof, where we've defined a1 equals 1, a2 equals 3, and an equals 2an minus 1 plus an minus 2. And similarly, b1 equals 1, b2 equals 2, and bn is equal to 2bn minus 1 plus bn minus 2. So these are called auxiliary polynomials. And depending on which real number we want to prove the irrationality of, we use different auxiliary polynomials, of course. And that's the difficulty. The difficulty is in finding these auxiliary polynomials. For root 2, when we put z equals root 2 over here, we found that that's equal to an squared minus 2bn squared. And we found that that's just equal to 1. For root 2, it was easy because we knew Pell's equation, minus 2y squared, and we knew how to solve it in integers. But for other numbers, it's not as easy to find the auxiliary polynomials. So in the next few videos, we'll look at the auxiliary polynomials which are used to prove irrationality of other numbers such as e and pi.